Yeah, thanks for coming to this week's meeting. So I'm going to be talking about this paper, generalized multi-agent reinforcement learning coverage path planning in unknown dynamic and heterogeneous environments. So I just came across this paper because I was looking at like PhD programs and like what people are working on. So I'm not an expert in reinforcement learning. I'm sort of just like figuring it out now, but I figured this paper seemed pretty cool and I'm going to try to explain it the best I can. So this is just the abstract. You can read it on your own. I can send it out. But I'll basically be going through like everything it talks about. The whole like framework is we're in a search and rescue situation. And so you might be someone is lost in some region, and instead of sending people to go find them, so that's very costly and also very dangerous. They're trying to work on having some sort of autonomous vehicles that can go out, search an area in some optimal way, and then try to find these people, and then you can allocate your rescue resources to them. Go get the person. So like yeah, for example, someone might be lost in like the mountains, and we're gonna get all these like quadcopters, which like you've probably seen them before. You have like remote control. You can fly them around. You have the four like spinny rotators. So you can send those basically like the region, and you'll just like figure out where the person is. But you want to do it like an optimal way because you might have like issues with battery life and like things like that. So you can't just like do it randomly and hope you find them. So the first like consideration is like how should we approach this problem? And you want to come up with a good way of like covering the area. So your vehicle has like all these sensors on it. And so what a lot of papers are doing is they're saying we have like say 3 or 4 sensors, and these sensors have different ranges on them. And so like let's just choose the sensor with the smallest distance, and we'll base like our search like zones based off that sensor. And the way they do that is like if you have some sort of like map, you can think of it as just like a 2D space for now. And you just put like a bunch of polygons on it, and then each polygon will be like a small search region that each like quadcopter can search. So like if your map was like Boston, you're trying to find someone, you can overlay like these polygons, which maybe are just like hexagons or squares. That paper actually uses squares. And the idea is if you put your quadcopter in the very center of your hexagon, it would cover the entire like region. And the way that works is its smallest sensor extends to the boundary. And so like you can imagine there's like a circle inscribed in your polygon. And yeah, so if you're at the center, like you explore that area of the map. And so now that we have like these points in the middle, we're now in this like graph framework where you have a bunch of nodes and are all connected by edges. So you want to think about like the most optimal way to go from the centers of all the squares with all your vehicles. That makes sense? Yeah. So yeah, just like before we can really like talk about how to approach the problem, just want to like get some terms established so like we have a common language. So basically we have the agents. The agents are autonomous vehicles. And this is the thing like we're using our reinforcement model and are going to be making these decisions on like where to go next, what area to go to. Then we have like the environment, so maybe the mountains or wherever your search and rescue area is. And then you have states. So that describes like the state that our agent is in. So if in like more complicated robotic situations, it might be like your left arm is at like this angle and doing this thing. But because we're kind of just like flying around, it might just be like they're in this location of the map. And then there's an action. So the actions we're considering are moving to a different spot on the map and also like turning. So there's going to be costs to turning. And you might imagine like on some maps, like there might be like it was on the original map, like a big area, like a box, but there might be like a tail that goes off somewhere and it kind of just ends and it's a dead end. So if you go down that dead end path, there's a cost. If it doesn't work out, then you have to go back. So there's some decisions to be made there. And then we want to come up with this policy. And that's what the whole point of like what some parts of reinforcement learning look into, basically coming up with this process for making the decision. And now we give the policy to the agents. So as they move around, they can make the next right decision. So this is another example of like what you might be doing. And now we're adding more specificity in how we're like splitting up our polygons. So like maybe you think the person you're looking for is somewhere in these windmills. So we mark those as green to say like we really want to make sure our robots go and cover that region. You might have out of bounds ones, which are red. So we don't want to go in there under any circumstances. And then these are considered hazardous. So you can see there's power lines or maybe people's houses. So you don't want to go in there, but if you need to, and if it's the most optimal, you might utilize going through like that area of the map. But you don't get an optimal score perhaps by going through there because you lose a little bit of points in this like function we're going to come up with. So in the paper, what they were doing is they used 1 meter long squares. So they just had like big room, bunch of squares. And then the distance to other squares are just decided by this L2 distance, which is just like Euclidean distance. They removed, so if like for those red boxes, they would remove those if you can't go there at all. And then for the green and yellow, the way it worked is if you like want to go to this coverage area, that's a positive value. So if you go there, you get points. And if it's there can even be like gradation among the green ones. So some are like more important to cover than some. So the more important they are, the more positive value. And then these dangerous ones, similarly, if it's like moderately dangerous, you give it some negative value. But if it's very dangerous, but still like you're allowing your robots to maybe go there, it would just be more negative. So yeah, that's how they're splitting up like the region. And then everything else is just free space. So like over here, they can fly over this part of the map without any cost. Yeah, and so then just getting more into the notation and being able to come up with some sort of objective function that we can optimize. Each node is labeled as Ni, so you can be at like the ith node. If you're connecting a node I and J, you have some sort of edge connecting them, which is called EIJ. And then for our quadcopters, we have M of them, so we have M agents. And then with all this in mind, we can come up with trajectory segments. So this will be when we start going more into the actual math. And the trajectory segment is an idea of like the cost of a certain like flight path and doing a certain exploratory action. So yeah, this is basically for at time t and given like an agent M, we calculate the cost of this segment. So you can see there's the cost of turning, and that's based off our current action that we're going to be taking. So maybe like we're going to decide now to go to this square, then also based off our last action that we just did. And then what this is the cost of going, say, like to another square. So it's I to J. So we're going from node I to node J with agent M at our particular time t. And then, yeah, let's see. We'll just pull up the paper. Oh yeah. And so then, sorry, the equation 2 here is just summing up. So at each, like, say your simulation takes like t time steps, capital T time steps, we can calculate the entire cost of this segment as being just the sum over all time. Okay. Yeah, and then in addition to that, we're gonna create this like extra, like the final cost of the agent. We're taking this trajectory segment, which is that. And then we're gonna add in like the cost of going into those avoid squares. So if you go into one of these yellow squares, we can calculate like at time 4, you go into that time, you get a negative cost associated with that. So we add that in. And that's just for one agent. So once we have like the cost for one agent's flight path established, we can now look at the reward for like all of our agents doing all these things. And so the important things to like include in such a function are going to be the sum of like each agent at time t. So just doing that. If you have any collisions, so the idea with that is like a collision is we don't want 2 agents going to the same region because we don't need 2 of them in the same spot. It's kind of redundant. If you go to any of these coverage spaces, that's positive points because that's what we want to do. And then they also wanted to include this term for the most costly trajectory of the group, which I'll explain why they're having both of these in just a second. But the idea is they're trying to distribute the work amongst all the agents. And also at the same time, they're taking into account the individual paths because they don't want like, there might be an agent who does unnecessary work that's not as bad as like the most costly path, but you're still adding in extra work that you needed, which might be clearer with the equation. So That's just like what I had in the last slide, but is the actual equation. So what you're doing here is you're summing up all of all the costs for the M agents, and that's over like at a particular time t. And then this term is what I was talking about with the most like maximum, the most costly trajectory. So, and then yeah, and then this is just like the collision. So if you have any two agents in the same spot, that you lose points. And then this is the reward function. So if you like cover a certain square, you get plus points, and then you're looking through. This is just a binary variable to say like if they went into the square or not. So they're saying like if any agent basically went into like a covered square, then you get the points for it. But yeah, back to like the point of having most costly and also each individual one. If you say you like didn't have this term, you might split up like the work among each individual agent and be minimizing that. But you could have someone that does some like really costly maneuvers while everyone else is not doing as much. Whereas if you just had the most costly one, you might minimize like the longest and hardest path. But you could have agents that like say that was like 20. You could have agents that would normally only be doing like 10, would only get like 10 points or something. But because like they're going and doing extra work that isn't worse than like the most costly one, which is 20, they might like do 18 for some reason. So that's why they have both terms. That makes sense, like the logic there. Yeah. Yeah. So now this is just for any like time t. We're calculating like, the reward of all the agents moving. And so now with that defined, we can look at the entire like search operation. So that's what the episode is. Like you have the situation, the whole episode is you're doing all these maneuvers over all time points t. And now we can calculate the final cost function, which then put into our yeah.
Sorry, so each time cycle, like each agent takes the same amount of time.
Yeah. Yeah. So the assumption is like at time, say 0, you have your agents in their initial location. They'll make like a say each one makes a decision to go to a new square. One like time step later, maybe that's 5 seconds. They'll all be in their spots. Yeah. So yeah, now I'm gonna just go through like calculating the final reward for like an entire operation, and then we can minimize this final objective function, and that'll give like the most optimal results. So yeah, and then just like the terms we're gonna be including is the most expensive trajectory, each individual ones, the joint reward for going through the nodes, like you want to cover as many like coverage nodes as possible, and then also try to avoid two agents being in the same location. And then this is just the point I was just getting at where like if you limit like the most expensive one, you tend to like distribute the work amongst everyone. But if you include the individual ones, you limit like individual excursions, like doing random stuff. Yeah, so this is just like the most expensive trajectory. So basically, like we're looking at all the time steps and the most expensive like move at each one. And we're just looking at the max. So that gets put in here. And then this is just the reward for covering those squares minus collisions, and then the cost of each individual agent. So you might be wondering why there's this 1/2 factor. The reason why they're doing that is to avoid what they call double counting. So the cost of say you look at the person or the agent who did the most expensive action, they'd be included in both those terms. So they want to put a 1/2 factor. But it's just a matter note. It won't really affect it too much. So now that we have this function, we can start using machine learning and reinforcement learning to come up with an approximation. So this is the part where I'm not as knowledgeable on how it works because I haven't used Q-learning or like OpenAI Gymnasium framework. But I can kind of go through what they were doing, and then maybe later on I can explain how to use these tools. But what they use in the paper is just a feed-forward neural network with two 64-unit layers, just in ReLU. And then the input was pretty interesting. So they used basically like they took their grid representation and they would put in like the current time states, like where all your agents are right now, and then one right before that. And I think the theoretical reason for that is they can approximate what's called a Markov decision process, which I started to look into, and I can give like a general understanding of what that is, which is on the next slide. So yeah, they basically have these like two inputs, like what we're doing now and what we just did. And then they normalize all the values, like they have include like where the agents are, and then they have another representation of the map, which include like basically specifying which squares they removed and which ones are terminal nodes or like dead ends. Yeah, that's everything. Oh yeah, and the other important thing they did is they treated each agent as homogeneous. So one of the limitations they have, even after doing this, is it's pretty expensive to train this model because the state space is like super large. So what they wanted to do is say like we're gonna treat every quadcopter as the same. And so like if you have some given like state space, like agent A is here and agent B is there, that's the same as having P in A spot, A and B spot, because they're the same agents and they're them being like swapped locations is the same thing. So doing that, you can kind of intuitively understand the state space is now like M factorial because you have M agents. There's like N ways to decide where to put them. But even with that, it's still like really hard to train. So when I show you the results, like they're on pretty small like grid spaces, but it actually is hard to train. Oh yeah, and then just like I don't fully understand the Markov decision process, but just to kind of give an understanding what that is. But yeah, I was just talking about what that. Well, yeah. So basically, if you have the current state and the one before, you can model this Markov decision process. And I guess the idea is you can produce like these joint actions, which are just how we're going to move everyone on the next step. And you can do that even if the environment changes. And then just getting like a little bit back into the math of like how it works. So like this looks like super confusing. And you can like get a really good understanding of it if you take stochastic processes, which I'm in right now, and it's really good. But basically, I guess the decision process relies on these two things. It's the idea that like if you have a bunch of decisions made over like say t times, so like you are in state one and state two, and you're in state t, you might be wondering like how do all these decisions we've made affect what we're gonna do next? And like maybe intuitively you can decide like, well, if you're like walking through like a maze of some sort, it doesn't really matter like how you ended up in like where you are right now. All that matters is that you're in that spot, and I can only like you only have like a couple options of where to go next. So where you're gonna go next is only dependent on like where you are now. So all these other decisions you made don't matter. So that's sort of the intuitive explanation of this like Markov property, which you can see it would hold in the situation. And then what this part is your well, this part is the probability of ending up in like this next state space, given like you're in this space now and you're making a particular action. So maybe to make it more applied to this problem, if you're in like this square now and you decide this action, what's the probability you're gonna end up in like the next square? And then the reward, this is like for the reward. So it's the probability of you want this reward in the next time step. What's the probability of getting that reward if you're in like this square, which is just like S, and you decide to do this action? So I guess using their inputs of having like the current state and previous state, you can see like having like where you are now and maybe right where you were before, if you can basically have the same math, like theoretical underpinning. So that's as far as I was able to get into it. It's like pretty complicated, but I guess you can model it as like a stochastic type process, which is kind of cool. And yeah, just to show like results and bring it back to Earth. So these are two different grids they did. That one's 6x6, and this is 12x6. And this is with 3 different agents. So using this learning process and these particular grids, you can see it does a pretty good job. Like this one avoids, well, they all avoid all the red squares. And then these two agents take a little bit of like penalty going in here and then clearing out those ones. And they end up at the end, which is pretty good. Which like probably is the most optimal way to do it, because if they didn't enter here, they would have to take all this time and going up and then back in and then back out. And so that's probably the most optimal way to do it. And you can see like similarly on the left side, they have really good results with hitting all the green squares and trying to avoid the like yellow hazardous squares and not going to the red at all. But pretty cool. And then just for fun, like they did it with real quadcopters. So like they also plotted like speeds, which is pretty high speed and cool. Yeah, so I figured I'd like bring this up. I thought it was a pretty cool paper. Um, and that's our prepared. So do you guys have like questions on anything? Yeah.
Yeah, sure. So, beginning, you can also talk about the way they do it was back to grids, like it's two squares or whatever the polygon was. So when, if you're looking at the mountain, like you're trying to search for the mountain, like it's not always a flat space. How does it work? I guess like through searching through that. Is that cheap ending at all?
Yeah, so I think the way it would work is you would treat it as like a 3D space, like a cube.
Mhm.
And it's the same idea as in each like cube, you have like a center. And instead of just being able to go like in the XY plane, you can go up and down. But they didn't do that because I think it's just they said even doing this was really computationally expensive.
Yeah.
So yeah.
For the markup decision process, is the goal like maximizing the correct decision properly?
Yeah, I think as like I laid it out, it's not necessarily clear like how you would maximize that. But I was reading an article where you can, I guess, use like Q learning and some other like reinforcement methods with this, and then you can optimize it. But that's something I haven't got to yet. Yeah, but you can totally use this to like optimize.
Is that what they're doing? Or is-
So yeah, what they ended up doing is they use this system called Q Learning and OpenAI Gymnasium framework. So the Gymnasium thing is basically you just can upload like state space and like the actual like layout of what you're looking at. And then I guess you feed that into Q Learning, which if you give Q Learning your neural network, it uses that as the approximating function. So in Q Learning, I think it uses something called tables. But if you decide to give it a particular model, it'll use that to approximate like your decision making steps. Yeah, so they weren't actually like directly using the like Markov decision process. I think they were just making a theoretical note like you can approximate it, and it's like similar to that. Yeah. Okay. Yeah.
Do they ever try like no research? But I'm thinking like in chess, right? They like look at the decision.
Yeah, they actually did do that. I didn't include it because I didn't like fully understand the equations, so I didn't want to like try to explain them and butcher them. But I can, yeah, they use Monte Carlo tree search, and they were relying on some like other papers, like particular uses of it to then augment this result. And yeah, that's in there. So if you're interested in like seeing how they did that, you can check it out. Yeah, yeah. So the way that works is basically like you can think of maybe like they do this right, and they get some sort of like when I'm at this square, I'm going to make this decision. But to make sure to like improve that decision, what they would do is basically like go down the tree. So if you're like, I'm at this state and I make this decision, that leads me to like these other squares where I can make these other decisions. And you end up making this like tree of possible things you can do next. And so what you can do is just kind of like randomly explore that tree, see like what the outcomes would be. And then you can back propagate back up the tree and update like how good your decision was, essentially. Yeah. So it's an interesting subset in a lot of like synthetic intelligence games decision making, where you can ruin like how good your option is. So like you see this a lot in like people who've used AI to solve like chess or Go, things like that. Yeah. Any other questions? Yeah. It's up to you guys. I don't know if you guys just want to get out of here, but I also have a video. So I noticed one of the authors, she was actually like featured on MIT's YouTube page, and there's some like articles written about her. So it's like 5 minutes. I don't know if you want to watch it. But that was cool. Okay. Sorry. Yeah. I'm gonna have to play the audio through my computer, I think.
When I was very little, I loved space. I loved Star Trek. And in the fourth grade, I stumbled across the term astronautical engineer. And I said, this is what I want to be. I've got a long history of family service. And so I knew I wanted to serve. So I went to the Air Force Academy. I majored in astronautical engineering. And my first 2 years on active duty were graduate school here at MIT. But I didn't have a great background, I found out later, in linear algebra. So my first semester here at MIT out of the academy, I got a B and a C. And for grad students, a C is basically you failed, but you tried, which just lit a fire underneath me. And that was when I discovered MIT courseware. I basically, on my own time, took what would have been 2 linear algebra courses in the span of about 2 months. And the next semester, I had an A and a B. And that B was the last B I got at MIT. After that, I went to pilot training. I did 7 tours of combat. I was injured in the middle of it, not related to combat, not related to my training. So I was medically retired, and at the time that I got out, I was doing poorly enough that I was not sure I was gonna live more than a few years. So that fourth grader who wanted to be an astronautical engineer, I was gonna take that all the way. And I knew I wanted to come to MIT. But I had been out of academia for almost 10 years by that point. So again, I knew I needed to get caught up to where the rest of my peers would be. So I applied to Auburn University to get a second master's degree in computer science, but I had no undergraduate degree in computer science. So I went back to MIT's OpenCourseWare and I took courses in computer architecture, networking, operating systems, algorithms was a big one, and having done really well in the program there, I think MIT finally accepted me. I work with small unmanned aerial vehicles or UAVs. We mainly focus on search and rescue type of applications. So we have 1 or more vehicles using a variety of different sensors, trying to train the vehicles in such a way that they can accomplish the task pretty much by themselves without any intervention. The stars aligned, I'm doing something that I love and that I hope will have a very positive impact. Not only my brothers and sisters still wearing the uniform, but everybody. Especially since I was physically unable to continue to serve. It means so much to see young people who are continuing to raise their hand and say, I'll put myself in danger in order to protect those that I love and the ideals that I love. And then, of course, you also want that sense of community with your fellow veterans. So working with student veterans and GA which is the Graduate Association of Aeronautics and Astronautics. I'm doing pretty well now. I found a diet and exercise routine that helps me control my symptoms. Throughout my life, I've kind of rejected being on the ground. I'm constantly looking for another way to be in the air. I found out MIT has a group that's doing acro yoga. Great fun, great group of people, all extremely flexible, extremely strong, very much engineering work with humans involved. So collaboration backwards produces something that none of us would ever have been able to make alone. You know, we're never physically designed to fly, but through human ingenuity, 1 step at a time, we found a way to do it. And so that's one of the reasons that I love OpenCourseWare is, you know, a lot of people who have taken big steps on that journey have now left something behind, a good foundation for other people to take the next step to something that's bigger and better than ourselves and in a place we could never get by ourselves. So that open-handedness when it comes to education is what drew me here.
Yeah, so that's all I prepared.